Hello everyone, today we're gonna continue our tree data structure part 3 out of 5. Extracting useful information out of tree using loop, stack, and queue. We're gonna need some context about tree data structure part 1 and 2, so please go ahead and check them out if you haven't done so. This tutorial is a part of the data structures and algorithm class. If you have taken the course Learns Everything About JavaScript in one course from SESV, you might recall that programming or computer science in general is having some information, and we as programmers or software engineers will process that information and output some useful information. So far in our class of data structures and algorithms, we have learned quite many ways to store, query, and search for our data. Today we're gonna use a combination of what we have learned to extract useful information out of the trees. Since this tutorial, we're gonna start learning some popular algorithms humankind has invented to extract useful information out of information. In our particular tutorial today, we will learn how to apply these algorithms to tree data structures. First, let's talk about motivation in real-life applications and also from coding interview questions. You can see that we have a binary search tree in this picture. It's the same tree that we have from the previous tutorial. Now if we take a step back and look at the tree in a very general way, the tree does not only store data in its nodes, but the nodes themselves have relationships to each other. For example, 6 is the parent of 4 and 8. And 4 is a child of 6. 4 is also a parent of 1 and 5. So if you imagine in real life, our tree can hold the data of a human ancestry tree. This layer of 6 represents the first generation. This layer of 4 and 8 represents the second generation. And this layer of 1, 5, and 10 represents the third generation. Then one of the query that we can have for our data is, how do we get all the nodes from one generation? For example, how do we get all the nodes for the second generation? In this particular tree, that would be 4 and 8. And we can generalize the questions that we want to print all the nodes in generations, layer by layer. For our tree in this example, that would be 6, 4, 8, and 1, 5, 10. That is one application about human ancestry tree. Let me give you another real-life example. Let's say our tree is representing the cost of car manufacturing and distribution. Our root node is the factory, and the cost to make a car is 6, and the rest of the nodes in the tree are representing the distribution centers. Each of the nodes' value represents the cost to take the car from the previous node to it. If we want to take the car from the factory to this distribution center, it's gonna cost 4. And if we want to take the car from this distribution center to this one, it's gonna cost 1. The further the distribution center from the factory, the higher the cost to take the car from the factory to there. And a practical question in this scenario is, if a user buying a car from this distribution center, or from this distribution center, or from this one, how much does the car cost? So if I buy a car from this distribution center, the cost will be 6 plus 4 plus 1 equal to 11. And if I buy the car from this distribution center, the cost will be 6 plus 8 plus 10 equals to 24. So those are the two real-life applications for tree data structure and the useful information that we want from it. You know, these kind of questions can be endless, and they inspire a lot of coding interview questions, like the list that you see here. Like 1, print the node layer by layer, 6, 4, 8, 1, 5, 10. Or 2, print all possible paths from root to leaf, 6, 8, 10, 6, 4, 1, and 6, 4, 5. Or 3, print nodes max values to min values, like 10, 8, 6, 5, 4, 1. Or we can reverse that, print mins to max, 1, 4, 5, 6, 8, 10. Or 5, print values by layers in zigzag order, 6, 8, 4, and 1, 5, 10. Or 6, check if a tree is a binary search tree, and for this one it's true. Or 7, return the biggest sum from a root to a leaf node. In our tree, that would be 6 plus 8 plus 10 equal to 24. So these are the 7 most popular questions that you can have with tree data structure. But there's more, and in reality, these kind of questions can be endless. So our question remains is there a simple, systematic way to solve these questions? And the answer is yes. But before we continue, I would encourage you to pause this video right here and briefly think about a solution of one of these problems yourself. If you do that, it's gonna help you to remember this pattern so much longer. I'm gonna give you 5 seconds to pause the video. Okay, I hope you gave some thoughts about it. Now there's a unified way to solve these problems. And the pattern is, it turns out that to solve these questions, we only need to do 2 things. First, we need to visit all the nodes. And second, we need to change the order of node visitation to the required logic. To visit all nodes, we have 2 ways to do so. The first way is using a loop, like a for and while loop. And the second way is using recursion. To change the order of which node we visit first, if we use loop, we can use stack or queue or a combination of both to control the order of node visitation. If we use recursion, we can change the position of the recursion call to control the order of node visitation. To really understand why we need to do this, we're gonna need to understand the difference between a human and a computer when solving problems, and that's what we're gonna do next. Now let's have a look at the difference between a human and a computer when solving problems. Understanding this difference will greatly help to translate human logical thinking into the code that a computer can understand and repeat. First, let's see how the human mind solves the problems. Let's say that our problem is problem number 1, print nodes layer by layers. That would be 6, 4, 8, and 1, 5, 10 in our human mind. When we hear the problem and we look at our tree, we look at the whole tree and we immediately know what the layers are. Just by one look, we have a lot of information. We immediately have the information of all the nodes and how the tree looks like. When we hear the request of printing nodes layer by layers, we immediately know which node to pick first, and also the sequence to pick the next nodes and the next nodes. For example, in this case, that would be 6, 4, 8, and 1, 5, 10. So that's how the human mind solves this problem. We look at all the data at once, and we know the order of what node to pick first. Let's take another example. Problem number 2, print all paths from root to leaf. When we humans solve this problem, again, we're gonna have the context of the whole tree by looking at it, and then we're just gonna pick the nodes in the order of the problem requested. In this case, that order is gonna be 6, 8, 10, 6, 4, 5, and 6, 4, 1. So that's how the human mind solves this problem. And if we keep going on our problem set, you can see this pattern as human gonna have a look at the whole tree and change the order of node selection to satisfy the problem requirements. That's how human mind works. Now let's see how a computer works. As you might recall, each node in our data structure is stored in the computer memory with a physical address. For example, node 6 has the address of 18, and the relationship between node 6 and node 4 and 8 are presented by the 2 pointers here. The left pointer is holding the physical address of node 4, which is 1, and the right pointer is holding the physical address of node 8, which is 23, and our tree root variable is holding the physical address of node 6, which is 18, and so on for the rest of the node in our data structure. When computers solve problems, for example, problem 1, print nodes layer by layers. By nature of the computer hardware, the computer CPU can only fetch and look at one data point at a time. You can think that the tree in reality is really big. It can have like 1,000 or million of nodes. By design, the computer will only look at one node at a time. In this example, the computer is looking at root node, which is 6, the node that the computer will start with to solve the problem. But then if the computer can look at one node at a time, how can we solve our first problem, print layer by layer? Well, that's where stack and queue come into the picture. So when the computer is looking at node 6, it knows where node 4 and node 8 are by the addresses. So with the first node 6, we can enqueue node 4 and node 8. Or if we're using stack, we can push node 4 and node 8 to the stack. Then when the computer finishes processing a node, in this example that can be node 6, the computer can dequeue the next node to continue processing. In this example, that's gonna be node 4. We can do the same thing with push and pop if we're using stack data structure to hold the next node to be processed. And let's say that the computer now is looking at node 4. It now knows about node 1 and 5 by these addresses here, and we can put 1 and 5 into our queue or stack. And by processing all the nodes in the queue or stack, the computer will look at all the nodes in the tree, node by nodes. So that's the difference between the human mind looking at the tree and the computer looking at the tree. That is, human mind look at the whole tree at a time, and the computer look at the tree node after node. That's the first step to solve our problem at human and computer, looking at the nodes. The second step is to decide the order of node selection. And for the computer point of view, the order of node selections is already decided when we choose either to use stack or queue to hold our data. For example, you can see if we use a queue, we are already processing the node in the correct order to solve problem number 1. So if we keep dequeuing, we're gonna have 6, 4, and 8, and then 1, 5, and 10. And if we use stack, we are already processing the nodes to solve problem number 2. We're gonna talk about these two in details later with some practical coding. So to sum up, when humans think about problem, we look at the data, and what we have is we see the whole data within the tree at a time. And the equivalent of the computer programming for that thought is, the computer will look at one node at a time, it will apply the logic for the only current node, and it will use loop or recursion to visit all the nodes. The second step for we at human to solve problem is node selection. And our action is we freely select nodes as we need, and the equivalent computer programming is we will use stack or queue, or a combination of both stack and queue, or multiple stack and queue to control the order of node selection. Or if we're using recursion, we can change the position of the recursive call to control the order of node selection. Next, we're gonna see how to use a while loop to visit all the nodes, and use a queue to control the order of the visit. A queue allows us to visit nodes layer by layer. It will start with the closest layer, and then expands to the further layers. This method is also called breadth first search, but we're not gonna worry about this name for now. We will have a dedicated algorithm tutorial for breadth first search later. So if we use the queue to control the order of visit, it's gonna happen like this. It's gonna start with the root node to the first layer and to the layers after it, one by one, and it's gonna print out 6, 4, 8, and 1, 5, 10. We will use a while loop to loop through this queue until there is no node left in the queue. Let's manually run this algorithm together. So our initial queue data is gonna be 6, our root node, and we're gonna have an array to keep track of our final result. For our first loop, we're gonna dequeue 6 and put 6 in the result array, and as we have 6, we know about 4 and 8. So we're gonna enqueue 4 and 8. Then our first loop is finished. For our second loop, we're gonna dequeue 4. So we have 4, and we put 4 in our result. And as we have 4, we know about 1 and 5. So we enqueue 1 and 5. And we finish our second loop. And as you imagine, if the loop keep going on, we're gonna have this result that we want. 6, 4, 8, 1, 5, and 10. Let's have a look at our practical code. Here I have the structure of the node, and we're gonna use binary tree data structure. Then we put data into our tree, and if we print it out, this is the tree that we have. This is our algorithm. It's gonna take in the root node. This is our queue, but the initial data is the root node. This result variable gonna hold our final result, and for easy referencing, we're gonna have a loop count variable to keep track of the number of the loop we have. So if we look at the queue data, initially we have 6. The while loop will run until there's no item in the queue left. And the processing logic that we have here will only process one node at a time. This is the key difference between a human mind and programming. So when we think, we think. But when we program, we need to think like a machine. Okay, so for each node, we're gonna print out a current loop count. Now we add the first one. As the first loop, if we look at the queue data, we only have 6. Now we dequeue. And if the node have the left child, we enqueue it. If the node have the right child, we also enqueue it. Then we store the current node data into the result. And if we print the result out, we have 6. Then we finish the first loop. Then the while loop start again, loop number 2. And in our queue, we have 4 and 8. We dequeue 4, we put the children of 4 to the queue, and we store 4 to the result. Then we finish the second loop. For the third loop, we dequeue 8, we put child of 8, which is 10, to the queue, and then we save 8 to the result. Then we finish the loop number 3. If we keep going on like this, our final result is what we want. 6, 4, 8, and 1, 5, 10. Next, we're gonna learn how to use the while loop to visit all the nodes, and stack data structure to control the order of node visitation. The nature of the stack, first in, last out, will allow us to visit the node from root to leaf first, depth first search. We will have a dedicated tutorial about depth first search later. Visiting nodes from root to leaf first, meaning that we're gonna visit root node and the child node and keep going on with the child until we reach a leaf node. In this example, that's gonna be from 6 to 8 to 10. This is our order of visitation if we use stack data structure. When we finish with one root to leaf, we're gonna keep going on with other root to leaf until we finish visiting all the nodes. So after 6, 8, 10, it will be 6, 4, 5, and then 6, 4, 1. That is the exact outcome that we want for problem number 2, root to leaf. So how it works is we're gonna use the stack data structure to hold our nodes for future visitation. So this is our stack, and we're gonna initialize it with the root node. We always have the root node at the initial data in the stack. We're gonna continue to loop until the stack is empty. For our first loop, we're gonna pop the stack and we have 6. We have 6 and we know about children of 6, 4 and 8. So we push children of 6 to the stack, 4 and 8 go into the stack, and then we save 6 to our result array and we finish our first loop. For our second loop, we pop the stack and we have 8. We have 8 and we know about a child of 8, which is 10. So we push 10 into the stack and we put 8 into the result array. Our result after the second loop is 6 and 8. You can imagine if we continue loop number 3, we will pop the stack again, which is gonna give us 10. Then we have the first path from root to leaf, which is 6, 8, and 10. That is how it's look like in high level. Now let's see how it's look like in our code. First, we have the structure of a node, and we have the structure of the binary tree. In this binary tree, we also have the search method. This method is gonna search for a node and return that node. You're gonna need this method later in our algorithm. Then we're gonna put data into our tree, just like our example. And if we print the tree out, this is our tree in the picture. Now let's have a look at our algorithm. We're gonna have our stack initialize with our root node, and the path variable will hold the current path from root to leaf. The result variable will hold all possible paths. We have a set of visited nodes to keep track of the nodes that we already visit. And we have the loop count variable to keep track of our iteration. If we print our stack out, you will see that the initial stack data is root node 6. Now let's have a look at the logic in our loop. It's important to mention that our loop is processing just one single node at a time. Just one node. This is the huge difference between a human solver and a computer solver. And we should remember this very clearly if we want to be a really good software engineer. Alright, let's start with our first loop. Loop number 1. And the data in our stack is the root node 6. So we pop the stack. We remember that we already visit this node. If our node have the left child, we're gonna push it in the stack. If our node have the right child, we're gonna also push it in the stack. So our stack right now has 4 and 8. Then we push the current node into the path. So our path right now is 6. The logic within this block is not gonna run until we hit a leaf node, which doesn't have any children. Then we finish our first loop. For our second loop, we pop the stack, which is gonna give us 8. And then we're gonna push the child of 8, which is 10 into the stack. And 8 is not a leaf node. So this logic is not gonna run. And our current path right now is 6 and 8. Then we finish our second loop. For our third loop, our stack data is 4 and 10. And we pop the stack, which is gonna give us 10. And we push 10 into the path. And because 10 is a leaf node, this logic is gonna be run. And we announce that we have reached a leaf with the path of 6, 8, and 10. Then we save this path into our result array. To do so, we create a deep copy of the path. Then we remove the last node from the path, which is 10 here. The purpose of removing 10 is to prepare the path for another child of 8. And because 8 doesn't have any other child, then the path from root to leaf through 8 is done. So we're gonna also remove 8 from the path. With 8 and 10 removed, the path is now only 6 and is ready to move to the next direction with 4, which is in our next loop. So with this logic, we loop 3 more times and we achieve our expected result, which are all possible paths from root node to leaf node. They are 6, 8, 10, 6, 4, 5, and 6, 4, 1. To sum up today's tutorial, we have learned the fundamental difference between a human and a computer when solving a problem. We also learned how to remove this difference by translating the human logical thought to the equivalent computer execution. And because this translation is a very basic thing in algorithm, You should practice and feel very comfortable using stack or queue to express your thoughts when designing an algorithm. This will conclude our tutorial today. Thank you for watching, and I will see you in the next video.